Welcome back to my YouTube channel. Today we'll be going over how to do data imputation on missing variables in linear data sets. So that means data sets that are basically always straight, always either increasing, decreasing, or flat between two variables. For example, if we look at gas consumption over time, usually that's always just a straight linear line because as as time passes, as you keep moving, gas consumption keeps increasing, right? And so we'll be covering ways to impute data that are limited to only linear data sets, and then some that are not limited to linear data sets. So specifically, we'll be going over linear regression imputation, stochastic regression imputation, and random forest imputation. And the two last ways, stochastic regression imputation and random forest imputation, can be used on nonlinear data, especially random forest imputation can be basically used on any type of data set that has some sort of relationship. But because I didn't have kind of a place to put these separately or time to make like a video just for them because it would be too short, I decided to lump all of these together. Yeah. So anyways, let's get started by first loading up some libraries. Or some packages rather. So we'll be loading in the tidyverse, and then we'll be loading in this thing called mice, which is basically an imputation package that lets us do all the imputations we're going to be doing today. So let's go ahead and run this. Okay, now that we have this in, let's go ahead and create a data set. Specifically, I want to create a data set that's going to be looking at gas consumption over distance traveled. Because, usually the more that you will travel in distance, the more gas you will consume with the vehicle. So to do this, we'll be we'll be calling a function. We'll be calling a dataset df. We'll be calling the data frame function, and we'll call one of the variables distance, and then it will be integers between 1 and 200 in increments of 1, and then we will also create another variable called gas consumed. And we'll be making this equal to a normal distribution with 200 data points, a mean of 20, a standard deviation of 5. And then here, we'll basically be adding this so that we create an ever-increasing linear relationship that is, instead of being flat, it'll just always be increasing, right? So let's go ahead and run this. All right, now we want to introduce some missing variables because we are doing obviously missing data imputation. And to do this, we're going to introduce this basic little bit of text here, basically saying that for the variable gas consumed, we're going to do a random sampling for all 200 of its data points, and we're going to pick 50 of those to introduce them as missing. And so 50 will be about basically 1/4, so about 25% of the data points will be missing. So let's go ahead and run this and see if it worked. So let's go into our df and see if we did indeed introduce missing values, and yes, we did. So we have all of these missing values that we will then impute in various different ways. And so I'm going to load up a bit of code here and then walk us through it. And so, like I said, we're going to be doing this in 3 different ways: linear regression, random forest, and stochastic. And so the first way basically involves doing a linear regression. So if you're familiar with that, it's basically just finding the line within the data that best fits the data, the line that minimizes the distance between, the line that is the minimum distance between all the data points, right? And so to do this, we're going to call a new data frame called data frame LM for linear model based off of our original data frame. And then we'll be using mice. And then specifically, we'll be using the method norm predict, which is just basically a linear regression imputation. And complete just means to not only find those variables, but then go ahead and impute them into all of the missing variables in the data frame. And then the second way we're going to do it is through using a random forest model. And we'll be using the same setup, creating a new data frame, for RF for random forest, called from the original data frame, and using mice and method RF for random forest. And then we'll be setting an M of 10 here. Basically, this is going to set how many different models we want to take together and then average. And so the more you have, the more computationally heavy it will be, but the more accurate it will be because it's going to be averaging more different samples. and then again the complete to go ahead and impute those variables into the data set. And basically a random forest imputation is basically just using a random forest algorithm that will basically predict missing values based on relationships between the missing data and the available data. It's a pretty complex algorithm. I'm not going to sit here and pretend like I know all of the math behind it. I just know that it takes into account relationships between missing data and available data, and then makes decisions based on that. And then the final way we're going to be doing this is through using a stochastic regression imputation, which is very similar to linear regression imputation. And we'll be doing something similar. We'll just be calling a new data set, which is going to be, SR for stochastic regression from the original data frame. And then the method will be norm.knob, which is actually stochastic regression. I'm not sure why they call it that. And then again, we'll be using an M of 10 to do 10 different samples that will then be averaged together. And then we'll be calling the complete function at the end, or the complete, not function, sorry, the argument at the end to be imputing those new found variables into the dataset. And basically the way a stochastic regression works is very similar to a linear regression, but in a linear regression, I mean, if you remember basic math, is that you're setting a single line and you're just saying, okay, this is the line of best fit, and then I'm just going to like impute along that line. It'll be a perfectly straight line of imputation, and you'll see this later as we're plotting the data. However, in stochastic regression, as the name may imply, it accounts for some stochasticity, some variability, some error, right? And in doing so, it'll introduce error into your imputed model that reflects the amount of error, or the amount of, not error specifically, the amount of variability or spread that is originally found in your dataset. So let's go ahead and run all three of these to create our data frames. So this will run all right. Let's let this run a little bit. Okay, so now we have our data sets. They all seem to be complete. Great. Okay, so let's go ahead and start plotting these. Wait, but first I'll have to calculate one more thing just so that we can look at the correlation coefficient of the post-imputed data, just to kind of compare and contrast them and look at them after the fact. So I'll need to create a function real quick. And this function is basically just going to allow me to calculate correlation coefficients for basically all of the data frames, because the data frames are just two variables, and then I'll be able to use that to plot them in our data, and we'll see which ones are more accurate, basically, right? And briefly, what this function does, basically, we're going to be naming it getCor for get correlation. We'll be creating a function based off of the data frame. And basically what we'll be doing is we'll call part of this from the, I believe this is from base R core. You can just do correlations in base R, yeah. And then we'll be basing it off the distance and the gas consumed. And we'll be using a pairwise complete observations. Basically, this will let us calculate the correlation coefficient in a way that will ignore missing data, because there are still missing data in the original data set, and so we need to set this in this way, and then we'll need to calculate the rest of the correlation coefficients the same way, or else we might get different values. And then after this, we'll be creating a label, which we will then be able to put into our visualizations simply by pasting correlation coefficient, which is the text that we want. And then we'll be calling the correlation coefficient, or rounding it up to two significant variables. So it'll be basically a 0.XX, basically, or 1, I guess, if it's perfect, but that shouldn't happen. And then we'll just return the actual label. So let's go ahead and create this function. Okay, so that seems to work. All right, so now let's go ahead and start plotting our different data frames. And so for this, what I'm going to do is I'm going to create a series of dot plots and a series of histograms, then plotting them side by side, so that I can then create one single visualization and then talk about it all together. And so for the dot plots, what I'll be doing is I'll just be creating, this visualization file, and then I'll be using ggplot, and I'll be using the geopoint function. I'll be using the data frame, and then, a distance by gas consumed. I'll be making this one black. And then these down here are just basically titles to put onto the visualization so that it's easier to read, except for this. In the subtitle, we'll be using the getCore function that we created earlier to show the correlation coefficient. So let's go ahead and run this, and then just check to see if it worked by plotting it, by actually calling the plot. Okay, so this seems to have worked. So now I'm going to go ahead and do just call the ones for all of the different imputation methods. And now, since we know that the first one works, we don't need to actually go ahead and look at these because we know it already works. So let's go ahead and just create these. Okay, that seems to have worked nicely. And now we'll be making some histograms to look at different data distributions. And to do this, again, we'll be creating a new visualization data using ggplot, again, using the data frame, or depending on which data frame we're using. And then X will be gas consumed, and basically all it'll be showing is the density or the amount of variables at specific given data points for gas consumed, right? And then we'll be calling geom histogram, and then just calling different colors, and these are all just basically little bells and whistles to make it look nice and standardized. So let's go ahead and create this and see what it looks like real quick. So what does it look like? Does it look okay? So it looks like it makes sense. Okay, so let's go ahead and create the three other ones. So I'm going to go ahead and load this in. So basically these are just all the other histograms for the linear model, the linear model here, the stochastic model here, and the random forest model here. And now we're going to combine these together using calplot. Oh, I think I actually may have forgotten to load up calplot, so let's go ahead and do that now. Library calplot, that's not bad. All right, so that should be loaded in. Delete that little bit of code. All right, so now I'm going to create this big combined plot together, and then we can have a look at it. Okay, so this might actually take a little bit of time to load, so I'm just going to run this and then pause the video, and then come back when it's finally loaded. Okay, so it has finally loaded, so let me just make this a little bigger. Oh, there we go. Okay, so what do we have here? Basically, we have our original data with all the missing variables. Then we have our linear regression imputed data in red. We have our stochastic regression in blue, and then our random forest in purple. And so there's something I want us to, there's a lot I want us to take a look at here. Let's start with the distribution of the data over here and all the histograms. So the original missing data distribution looks like this. Now, the fact that there's 25% of the data missing is not actually going to affect what the distribution looks like. It's not going to affect how the distribution looks like because they were randomly sampled, right? And so now let's look at how different types of imputation affected the distribution. And so if we look at the linear model here, we see that, for the middle variables here, they're all rather high. There's a big sort of overrepresentation of, middle, median, mode data points, and that's exactly what you would expect in an imputation type that basically figures out what the general trend is and imputes all of the data along that trend line, right? And in fact, if we look in the dot plot on the left here, we can kind of pretty clearly see a line, sort of running through the data set that's just, one straight line of imputed variables. And if we look down at the stochastically imputed and the random forest imputation, this sort of distribution of overrepresentation in the middle is, more or less gone, right? Like if we look at the original data, there's kind of this little ramp up here and then this little ramp down, and there's a little ramp up here and a ramp down here that's almost kind of identical here, right? So in these cases, using stochastic regression and random forest imputation has sort of given us a more true to life, I guess I would say, data distribution post-imputation. And if we look at the dot plots, again, I did allude to this earlier. This one very clearly has like a straight line just running through it of imputed variables, but you can't really see any sort of obvious pattern that has emerged from the stochastic regression imputation or from the random forest imputation, right? And that's kind of what you would expect because it's not following any set rule as it's doing it. And so another thing I want us to look at are the correlation coefficients. The original missing data has a correlation coefficient of 0.78. However, the linear regression imputed data has a correlation coefficient of 0.82, which is kind of what you would expect if you're kind of forcing more of your data, so in this case 25% of your data, to follow more or less a perfectly straight line. However, both other models have 0.77, which is much closer to the original one. And again, while 0.82 might be a quote-unquote better correlation, that's not what we're looking here. That's not what we're looking for here. Here we're looking for data imputation that better reflects the original data set. And in this case, the stochastically imputed and the random forest imputation much more accurately reflects the original data. And for this case, in a case where your data is sort of, your original data set is not like a perfectly straight line, these are going to be much far superior imputation methodologies, right? However, if your data set is extremely highly correlated in the beginning, it's not really going to make a difference. And actually, I'll show this to you. And the way we're going to do this is we're going to go back to creating our data set. And here, instead of setting a standard deviation of 5, which is rather big, we'll set a standard deviation of 1, which is rather conservative. It's a standard deviation that's going to be very narrow. And I'm going to predict that in this case, what's going to happen is most correlations are all going to be roughly the same, and it's not really going to make any difference because all your data is pretty much the same anyways. And so let's go ahead and rerun this entire bit of code. Should finish rather quickly. Okay, good. And now I'm going to reopen the combined plot, pause the video, and get back to you when it has all fully loaded. Okay, it's fully loaded, and what do we see? We see that basically all of them have a correlation coefficient of 0.99, which makes sense because all the data is has a standard deviation of 1. It's not really going to vary too much, so there's no real reason to be favoring one type of imputation model over another. And if we look at the distribution of the data, it's basically more or less the same for all of the different styles of imputation, right? And so choosing an imputation method is going to vary basically based on how variable your data is and how much computational power you're willing to put into this. Now, this was a fairly quick thing because there's only, what did I do? I did 200 observations. But if you're having to integrate, filling in missing variables as part of a long automated data script, factoring in how long this step is going to take is going to be a significant part of your ultimate decision into which model you're going to be using. And so your decision to use a linear regression model will, require far less imputation, but will be less accurate, whereas using something like a random forest model will be much more heavily computationally, but far more accurate if you have a lot of variability, whereas using something like a stochastic regression will be, somewhere in the middle where it's it'll be far more accurate than linear regression, but it won't be, as computationally heavy as a random forest model. And that's something you'll have to take into account and balance yourself as you're kind of building your products or building whatever it is you're working on, especially if you're going to be dealing with A, automation, and B, data sets that may have thousands or tens of thousands or even hundreds of thousands or even sometimes millions of data points to look through and then clean and then make assumptions about. But yeah, that'll be something for a future video or a future topic. But yeah, that's all I have for today. Next, my plan is to go into another final imputation method that is much more useful for, I don't want to say real data sets, but data sets that have, that are a lot of variables. So for example, if you're working in finance or working in HR, where you might have, 5 or all the way up to 20 different variables about, a single client or a single company or a person or something like that. And then you notice that there's a bunch of missing data. You can actually impute that data using a method called hot deck imputation, which is what I'll be covering next, based on all of the other data that are not missing that are, already available. And so you'll be making a very accurate, snap, quick decision that's actually computationally not super heavy because you're only using your own data set to just kind of fill things in a predictive way. So that'll be the topic of my next video. I think it'll be super interesting because personally, I really like using hot deck imputation. I think it's, for everyday use, it's probably the most useful sort of data imputation method you can use, because it's quick and it's effective and it's computationally, rather smooth. So that'll be the topic of my next video, and then I'll be going into cleaning some string variables, and then that'll complete all of my mini video series on data cleaning, and then I'll cap that off with a full data cleaning project, which, I mean, you can follow it through and have that as a data analytics projects for your own portfolio if you wish. So that's my plans for my future videos. I hope you enjoyed it. If you have any questions, drop them down in the comment section. I'll be posting the code, the annotated code, I'll be adding a bit of annotation into it, down into the description. So yeah, still don't have an outro. So yeah, have a good day.